Any problems with the homework? Yes, no, maybe? Okay, shall we work on them in class quickly? Okay. The first problem was we had a 50 Pascal amplitude. Sound pressure wave incident normally in water to air. Okay? And we are asked to find what is the transmitted sound pressure, what is the intensity, and then the intensity difference. Okay. Now, the information you need are the specific acoustic impedance for all three, your homework, for all three. For air, it is 450 Pascal second over meter, and for water, it's a bit larger than that, 1.5 10 to the 6, of course, same units. Okay, thank you. Now, you can redrive this, but the transmission coefficient, which was PT over PI, is, you remember this, okay. And here, rho 2, C2, rho 1, C1, meaning the ratio of the transmitted side to the transmitting side. So that would be rho C air to rho C water. And that's, that ratio is roughly 10 to the minus 4. And if you substitute it back here, the transmission ratio is and since we know the amplitude of the incident wave, the transmitted wave would be, oops, which is roughly that would be the approximately the solution. Okay? Now, questions asked about the intensity. As you know, intensity is for a plane wave. Intensity is defined as so if you substitute the incident intensity would be watt per meter square. And similarly, let me clean this up. The transmitted intensity would be And the last part is, what is the reduction in decibels?
Can I ask you a question?
Sure.
While finding the intensity of the incident wave, we use the impedance of the air, but I think we supposed to use.
Oh, I'm sorry, you're right. It is not. It's always the other one. It's 1.5, sorry. Oops. Yeah, okay.
And can I also ask another question?
Yes, let me just make sure that everything is correct here. It should be okay. Yes.
For the last part of the question, you said that we are supposed to find the difference between
Mm-hmm.
but I think it's asking that what is the transmission coefficient? I tried to find transmission intensity coefficient.
Expressed, yes, that's correct. And that is a difference in dB. Let me just explain. Transmission coefficient for intensity is 10 log okay, that's a definition.
I tried.
Okay.
Actually, I found intensity of the incident wave in decibel, and also I found the intensity of the transmitted wave in decibel, and I found the ratio between them.
No, you can't. Well, see. Yeah, but you can't. You do not take a decibel ratio. 10 dB divided by 50 dB, for example. That's not the way it is done. If you look at this now, this also can be written as okay. You can see that it does become, this is the same as their difference. So if you put it here, let's see. And that's something like 29.5 dB, I believe. Is that correct? Yeah, something like that. See, this is from the definition of decibels, it's a ratio, power-like quantities. And then that would straighten it out. Any other questions on this? Yeah, okay. Where did you miss? If you missed the answer, what was the weak spot? Where did you miss it?
We really try to understand, first of all, 50 RMS.
Oh, you tried to understand it? What was it?
The definition of where did it come from and what should we multiply by, that by square root 2 or something?
Oh, I see. Okay. No, these definitions usually use the RMS value, the effective value, rather than peak, because usually that's what you measure. Okay. So in all of those. And secondly, when you take a ratio, it really wouldn't matter anyway. Okay, because you multiply both, so it doesn't matter. What else did you miss?
And what for me leads me to at the last part?
This part about the ratio dB. Good. Well, part of this is identifying what we're missing along the way. So you're learning something a little bit different. Okay. Now the second one was about the ocean floor. The plane wave is reflected from the ocean floor at a normal incidence at an amplitude 20 dB lower than the incident wave. Okay. So the question here is, you're in the ocean, and inside the water, you send a plane wave, and you have a reflected wave. And it says that reflected wave is 20 dB. Let me make this minus. Okay. 20 dB less than the incident wave. So what are the possible values of specific acoustic impedance of the soil? Now, I know you had difficulties about what are. Why isn't it a single value? Even if you were asked a single value, it's more than one because there are two values to it. And so this expression you can also write as 20 log amplitude PR minus 20 dB. And of course, this is okay, so okay, so it's 1/10 the value of the other one. And we have, from our original derivations, that the ratio, the pressure reflection coefficient can be defined for normal plane waves, not for everything else. It can be defined only in terms of the ratios of the specific acoustic impedance of both parts. Okay? And since we have R plus minus 1/10, see, this is the key. The absolute value gives you plus or minus 1. And that gives, of course, two different possibilities. Or okay, so you have just two different values. These are straightforward problems. The last question was, again, very similar. You have a plane wave traveling, I think it was from air into hydrogen. Which is separated by a membrane. We assume here that membrane is so thin that it has no effect on the acoustics, and that's a legitimate assumption. So, and it says plane waves traveling from air into hydrogen across the membrane, and it's refracted by 40 degrees from its original direction. So it's not a normal incidence. So this is 40 degrees. This whole thing would be the transmitted angle. Okay? And so the question is, what is the angle of incidence in air? And what is the sound pressure transmission coefficient? So once again, for air, something like, it should be really 415. Let's just use a standard value. But for hydrogen, the specific acoustic impedance is 114 Pascal. But one needs to be careful here. The speed of sound for hydrogen is much faster than it is whereas 343. Do you have all the information now to be able to solve the problem? Okay, so what is the first thing we do? We find the relationship between the incident and transmitted angles in terms of the ratios of speeds of sound. Okay, and here you can write the transmitted angle as sine theta I plus 40, and after that it just becomes a matter of simple mathematics. And if you just make the appropriate substitutions from here, you'll find that theta I is something like 12 degrees. Okay, so 12, 13 degrees, depending on how accurately you calculate these. And what is the next part? What is the sound pressure transmission coefficient? Well, I think we have solved this in the last one. Okay, so I think you can handle that as well. Any questions on these? These are straightforward. All right. Let me erase and then start today's lecture series. We will cover the. Let me give you an outline. We will cover acoustics of waveguides. And let me just show you what we'll start doing. Okay. What we'll do now is we had been talking about plane waves in free, unrestricted medium going and maybe at a normal incidence to a boundary or at an oblique incidence. But now what we want to do is see what happens when the plane waves are traveling inside a boundary. And if they are at an angle, we'll learn, number one, what it means to have a cutoff frequency. This is just an overview of this whole topic, okay? I'm just summarizing now what are some of the things that we're going to cover. And so, first thing we'll talk about is a two-dimensional wave propagation in a channel, okay, in pipes, ducts, etc. And then we'll learn about cutoff frequency. And then we'll talk about radiation below resonance, below first radial resonance. Again, what that means is this is the radial direction, okay? And the first resonance here is what is the cutoff frequency for that mode. And below first radial resonance, it's all plane waves, just like we have seen before. Sound will be radiating straight down. Well, what happens then if you have a pipe that's flexible? You have air conditioning ducts, for example, or you have hoses, you have plastic materials. If this is flexible, okay, so flexible walls, what do you think happens? What effect? Think about this just for a moment. What effect flexibility of these walls have on sound propagation? Say again?
Resilient.
Resilient, but it's a wall, it's flexible, it's not open. And if it's open, then of course it's a free environment. Yes? The question is, you have a channel here, let's say a duct, and sound is propagating. But if these are flexible, what happens as opposed to being rigid?
You're writing you is equal continuous for both sides of the wall.
Mm-hmm.
Now I think we can write that, or is
What you should think about is sound is a pressure wave going through. Pressure means pressure times an area is a force, okay? So here, as sound is traveling, a force is acting on the sides. But because these are assumed to be rigid, it makes no difference. But if they're flexible, what will happen to them? They will start flexing, okay? Now, how will they flex? Because they have some inertia, some flexibility, it's like an oscillator. And if they flex, what happens? The volume or the area is going to change. If the area is changing, the instantaneous volume changes, density drops. So the pressure equation is going through a transformation through the flexible area. That's what we'll learn. What does it mean? Now, there'll be resonance of the pipe. You hear these sometimes, okay? So that's the flexible walls. Well, another thing is, what would happen or change of area? Suddenly, you have from one type of duct, you go into a larger area, or vice versa. You come from a large area into a small one. Suddenly, similarly, the area changes, the impedance changes. Then we have acoustic transformers. Transformers. Do you know of an example? Can you think about one? What could be an acoustic transformer? Loudspeakers. Right? How sound is radiated from it. Do you have a diaphragm here? Which is a certain area, comes into a smaller one, and it radiates out. So these are loudspeakers. And then you would have, let's say, in a pipe, you have silencers. Have you seen a silencer before? An acoustic silencer? No? Yes, you have. Yes, mufflers in the car. The muffler that's under the engine. So, for example, mufflers. That's exactly what they are. They are acoustic silencers. And you can add these silencers in factories, for example, where they have a chimney that makes a lot of noise, air conditioning noise, and so on. Anyway, and then at some point, we'll cover the non-planar terminations. Oops. terminations, meaning you have a duct, and we have always looked at either rigid ending or open. But what happens if you have a non-rigid termination, or if you have something like this, or if you have something like this? Okay, so we'll take a look at all these. So acoustics of waveguides covers a number of different topics, and we'll now start with the very first one and drive the equations of motion. So first, wave propagation. Can you read this? Is the size okay? All right. Wave propagation in 2D waveguide. Okay, let's consider this waveguide. The walls are rigid. The lower wall is on the x-axis, and the normal to it is in the z-axis. It's the cross-section is between 0 and L. And it's infinite in y direction, meaning it's completely open. Just consider two infinitely wide surfaces, okay? So we're not concerned about the boundaries coming out and into the whiteboard. And the pressure equation that's traveling in the x direction can be written as before. Sorry, let me just, this is x and z. This is z. These are correct, as you can see. Okay? This is in the x direction and propagating in the z direction. So in x direction, you have one wave going in the positive x, and the other one is reflected back with general amplitudes a/2, b/2. The reason for 1/2 will become obvious in a second. It's just part of the constant. I could have made these a/10. It doesn't matter. So it's just a constant value. And as before, you can see I can utilize A here for to get the cosine here. Okay, now for rigid walls, the boundary condition is the particle velocity is 0. The particle velocity is 0, and that means the gradient of pressure is 0, and that gives us complete. This is the first boundary condition, and the second boundary condition at the upper surface gives us another relationship, and that is now this is becoming an important parameter. Let's see now. Okay, this value here, okay, that gives us now, what this says to us is, I think I used just L. What it says to us is, for this equation to be satisfied, this condition must be also satisfied, okay? So this gives us permissible wavelengths in extraction. And if that's the case, let's go back and rewrite the equation of motion. The pressure equation. The pressure equation will be then a sum of this now becomes the equation that represents pressure that can be transmitted through a waveguide, okay? And so not any old wavelength can go through, and it has to be one of those. And this is now a summation of all the possible wavelengths, okay? Any questions so far? You follow all these? Okay. Now, there's an interesting issue here that is we remember the components of the wave number. Their sum, the squares of their sum of their squares should be equal. Okay. Now from here, all right, this is a very fundamental result that you need to be aware of, okay? You need to understand this because this is an essential part of sound propagation in channels, pipes, ducts, etc. And why is that? What do you see here that's unusual, that's important? What does it say? You probably will see it if I write it slightly differently. Oops. Now, do you see something unusual about it? What does it say? Number one, what is KZ? What does it represent? Take a look at the equations. Come on. This is the pressure that's traveling in a waveguide. Okay? And we now have an expression. This is not a free number anymore that you can just select. It has to have a relationship that has something to do with this length. Okay? What else? It can be imaginary or real. Yeah. It can be imaginary or real. So if omega over c squared is larger than kz is real, and if it is real, then it's a propagating wave. Okay? However, if it is less, then it's imaginary. Now, if it is imaginary, let's just take a look at this for a moment, just for a second. You can see that pressure, just taking that particular component and substitute an imaginary value, you can see it dies away exponentially. Okay? So if it is at a frequency that's less than a corresponding mode, that will not travel down to far field in the waveguide. And it becomes what is called an evanescent wave. It dies out very soon. Let's see what that all means, okay? Let me just rewrite the same equation. Okay. What I have done now is substitute kz with an expression that says kz sub m. Why is that? Because as you can see, it depends on m. M being the mode number, okay? And it does come from this relationship, original relationship that says these are the permissible numbers, okay? Permissible numbers to satisfy the boundary condition. So continuing then with that description for waves, just to summarize, to propagate in z direction, kz must be real. And for kz to be real, that means k must be larger than kx, k being omega over c. And that means frequency must be okay. As you know, this is omega over c, and this is m pi over Lx. Now, what happens if m is 0? Because that's one of the permitted values. What's m equals 0 mean? Just think about it. You have all the information on the board. What's m equals 0? Think physically. What happens? You have everything. K is always real, and it equals what? Say again? K is always the kz is always real. Yeah, go ahead. Correct. See, when m is equal to 0, kx is 0. What does that mean? There's no propagation in the x direction. Okay, so there's nothing in that direction, so everything is along the z-axis. Okay. And let's see now, let me. For M0, just to complete this, real. Exactly, and it propagates always in the other direction. But for modes, larger than 1, the wave number, let's see now, let me just do this quickly here. Okay. Let me explain just what is important here. Okay, and what is important here is for a certain mode number, there's always a frequency, okay, that must be larger than this value for that mode to propagate. Otherwise, it will not propagate. What do we mean by mode? If you look at this, in the first mode, when it's a zero mode, it's a plane wave. Pressure is the same all the way across. But when it's m equals 1, then you have, the mode shape that's pressures are maximum at the wall. And then this is M1. M2 would give you something like this, and so on. Okay, so these are the mode shapes in the X direction. For that shape to be able to travel, okay, for the sound wave in the X direction, to have that mode, to be able to travel, frequencies must be larger than the corresponding frequencies. Okay, in other words, for let's say, what did we say? This is m is equal to 2. For a sound wave in the X direction to have this shape to travel, omega 2, okay, must be larger than m pi LXC. Because that would be the cutoff frequency for that mode. Okay? Does that make sense? And what does it mean to travel in this shape? So if you have a particular frequency, omega 2, that has this value, then you're able to transmit a shape like this. And that also means when you have a microphone, as you traverse it up and down, you'll have a maximum here, you'll have theoretically 0 here, maximum 0, and so on. Do you understand what I'm getting at? It's because the waves also reflect up and down, okay? They have interference, they cancel at 2 points for this mode. Okay, does that make, can you, in your mind's eye, see the difference? Yes.
In between those modes, are all the waves
In between, it doesn't travel. You resolve it into those modes. It's like Fourier transform. It just does not, you're not able to satisfy the boundary conditions. So if you excite a wave in between, that's a very good and legitimate question. If you excite a wave between, let's say, omega 1 and omega 2, okay, you have just some frequency. Only some parts of it will travel, but not all. Okay. Okay. Why don't we take a 2-minute and let me clean the board and continue on this.